Let's go back to another iconic bridge or structure. So this is Millau Viaduct. French is very complicated. I will not attempt to pronounce it. And this is very, very unique structure once again. It's a cable-stayed bridge which is not unique, but the uniqueness is in the number of spans, number one, and secondly, the beauty of the bridge once again, and the height of the bridge, and the way it was constructed. So this is world's tallest bridge, as you might know already. And once again, this is a cable-stayed bridge is a evolution from the suspension bridges. As you know, we instead of using the suspension, we use the cables directly to hold the deck up and producing horizontal force into the deck. And so this is quite well known. So the problem was that in this road that you see here, it was before this bridge was built, people have to go down into the valley and come up. And this is going from Paris to the ocean side. So a lot of traffic. So there'll always be a traffic jam passing through this valley that you see here with a narrow road. Hours and hours, people will get stuck. So they decided to make this bridge to cross the valley straight away. That's where you see that bridge located. And there was a lot of discussion on what we should do. And then they decided to make just a very straight bridge. No, some people said, oh, we can maybe go down a little bit, reduce the height of the tower. But then they said, no, we'll just make it very straight. Don't need to do that. So then they come up with a very nice arrangement to do that. So this is the view from there. It's the 7 pylons. It's quite long bridge. They're very slender, very elegant. You can see the height. It's like taller than most tall buildings. And the piers themselves, concrete pylons, they're very, very tall, freestanding. And on top of that, you have steel deck. And then you have steel pylons and steel cables. So it's a composite system, beautifully executed, absolutely beautiful in its form and its scale. So what is most important is this. Normally, the bridges, cable-stayed bridges, are made in such a way that you make the tower first, and then you hang the deck from that side, and you incrementally hang the deck on both sides by adding cables. So you make the tower, hang one cable on each side, put the deck, hang second cable, and so on. So you construct outward from the towers. That's the normal procedure. But here, they couldn't do that because towers were so tall and it's impossible to do that. So they decided to launch the bridge from the two sides, just like a launching of the box girder. But this is not box girder, and the span is much longer. So what they did was they constructed the one tower and one deck on ground and then started pushing that span as a launching nose. And let's see how that worked. So if that is the bridge to be constructed finally, that is the way it looks like, they actually did something like that. They put intermediate temporary supports in between every place except in the middle where there was a stream. They couldn't do that. So they put everywhere 7 temporary supports, and then they use from both sides, they slide this bridge on top of these temporary supports until they meet in the middle, and then started erecting the towers and hang it from there. So it's a very interesting concept.
It was necessary to create a system where the launching force was created pier by pier in such a way that no force, no bending was produced in the piers.
As the two colossal sections approach each other from opposite sides of the valley, above the Tarn Valley,
so you can see here, this is very interesting, unique idea. You construct the one span with the tower and then just keep sliding, and the tower will keep that cantilever up, and you slide it, and then after it's complete, put the cables, remove the temporary supports. It was just brilliant. But it required precision that you cannot imagine. Almost 1 kilometer from each side, it meets in the middle with almost no error, maybe 10 millimeters error. This is unbelievable. So this is how it was constructed, as you can see from here, from the diagram on the left-hand side. So the towers were made first, and then the temporary support, from the left side, the bridge is pier. Look at the figure in the middle here, where you can see that during the construction, the deck has a lot of deformation because there are no cables to hang it. So the deck is flexible, so it's deforming a lot between the temporary supports and the actual supports. So when you have the cables, they tension the cable, this will become straight. So they accepted that deformation. Secondly, look at the tower. The steel tower is being rolled, huge tower is being rolled on two trucks, one truck at one end, one truck at the other end, and they take it in the center, they raise it up and then pivot it and attach it. It's just like a Lego piece, but the size of the tower is huge. It's very tall and then weighs several tons, 100 tons. And they bring it and they just make it as if it is made from some small piece of wood, and they install those towers. And these towers are installed after the bridge deck is already complete, which is very unusual. So that's how they did that. And this is some of the process, cable tensioning, all of that is being done. And here is the designer. Once again, many people think that Norman Foster is a designer. People call it Norman Foster's masterpiece. But it is Michel Virlogeux who actually designed this, who has designed over 100 bridges. And he's the one you saw in the video explaining how it's done. But to win the project, he also invited Norman Foster to do the architecture, do the coloring, do the pylon. So pylon design was done by Norman Foster, and the color scheme was chosen by them to make sure this architecturally looks beautiful. But all of the engineering was done by Michel. So that's another area where you can see the structural engineer less well known than the architect who just contributed on the form in some way. It's unfortunate that many bridges now architects come in and make them aesthetically better. It used to be buildings, but now it's also many bridges where architects get involved. And that's why I think engineers have to learn aesthetics as well. So that's his work. So he is one of the world's leading structural engineers, designed over 100 bridges. You can imagine 100 bridges, a lot. And he designed this viaduct to be very light, and he conceived the launching system. He designed the whole system, and then he was there at the site when they finally also connected that. And the bridge cross-section is streamlined, it's very lit. On the side, it looks very thin because the box girder, as you saw here, if you see the box girder here, on the edges is very thin. So from the side, when you see it, you don't see the depth of the girder, and it's aerodynamically very smooth. So let's hear
A 3-year adventure for 500 people.
Each bridge is a prototype. You use ideas which generally already exist. An engineer must know what was done before and must be able to reuse the good ideas which exist. A colleague said, engineers are climbing on each other's shoulders.
And that's exactly the reason we are doing this webinar, because engineers must know what has been done before and why, so that we can build upon that and we can continue and innovate and add our own thoughts and our own improvements into the system that have been developed by other engineers. And every time we see happening over the years.